Okay, friends, we have seen in the last few lectures how to compute eigenvalue of a given matrix. Before that, we have seen what is the eigenvalue of a matrix and what is eigenvector of a matrix. The moment we are talking about eigenvalue and eigenvector, it must be clear in our mind that we are talking about only for a square matrix. If a matrix is not a square, then we cannot talk about its eigenvalue and eigenvector. So, if you recall the meaning of eigenvector and eigenvalue of a matrix, we have seen that if A is a square matrix of order n, then a scalar value lambda is called eigenvalue of the matrix A if we can find a non-zero x which will satisfy the relation A x is equal to lambda x. Meaning thereby we have seen that if you take the matrix A, from here you subtract the matrix lambda into I, where I is the identity matrix and its order is exactly same as that of A. Then you operate on x and see it is equal to 0. So, this is a linear and homogeneous system of equation. So, whenever this linear and homogeneous system of equation has a non-trivial solution, non-trivial solution means is there any x which is different from 0 and which satisfy this relation? If yes, then the value of lambda corresponding to which we are going to get a non-zero solution of this equation A minus lambda x is equal to 0 is called an eigenvalue of this matrix A, and this non-zero solution x is called eigenvector. This part we have seen long back. If you look at some very standard and useful results, suppose matrix A is given and its eigenvalues, all eigenvalues are also known to us. So, suppose lambda 1, lambda 2, lambda n, these are the n eigenvalues of the matrix A. These eigenvalues may be repeated, need not be distinct always. Then what is the determinant of the matrix? Without calculating the usual process, without going through the usual process of calculating the determinant of a matrix, only if eigenvalues are known, then we can see immediately that determinant of the matrix is the product of the eigenvalues, product of all eigenvalues. So, determinant of A will be lambda 1 into lambda 2 into lambda 3 and so on so forth into lambda n. So, remember, if eigenvalues are known, if all eigenvalues of a matrix are known, then the determinant of the matrix is also known, just it is the product of all eigenvalues. Similarly, if all eigenvalues are known, then we can see immediately what is the trace of the matrix. Trace of the matrix means sum of the diagonal elements. Diagonal elements means we are talking about the principal diagonal. Sum of the diagonal elements or principal diagonal elements of the matrix, that is again is equal to sum of the all eigenvalues. So, if lambda 1, lambda 2, lambda n are n eigenvalues of a matrix, then trace of the matrix that is sum of all diagonal elements, or precisely we shall say sum of all principal diagonal elements, that is A11 plus A22 plus A33 and so on so forth plus ANN will be equal to sum of the eigenvalues, that lambda 1 plus lambda 2 plus lambda 3 and so on so forth plus lambda n. So, these are very useful result. If eigenvalues are known, then we can immediately tell about two things: what is the determinant of the matrix and what is trace of the matrix. Not only this, look at here, this is called shift result or shift theorem, in fact, that if eigenvalues of A are known, then eigenvalues of A minus ki is also known. That is, suppose eigenvalues of A are lambda 1, lambda 2, lambda n, and A minus ki, where k is any real number, then what are the eigenvalues of A minus ki? So, this is again lambda 1 minus k, lambda 2 minus k, lambda 3 minus k and so on and so forth, lambda n minus k. Okay. So, suppose that 0, 1 and 2. These are 3 eigenvalues of a 3 cross 3 matrix. Okay, these are the eigenvalues of the matrix A. And now suppose you are having A minus 3i. What are the eigenvalues of A minus 3i? So, what is the eigenvalue of A minus 3i? 0 minus 3. 0 minus 3 means, so lambda 1 minus k. So, 0 minus 3, that is minus 3. Again 1 minus 3, that is minus 2. 2 minus 3, that is minus 1. So, 0 minus 3, 1 minus 3, 2 minus 3, these are the eigenvalues of A minus 3i. So, therefore, if eigenvalues of A are known to us, then eigenvalues of A minus ki is also known to us for every real number k. Look at here, the main purpose of this lecture is something different. We know how to compute eigenvalues and eigenvector. Okay. In this talk or in this lecture, we are going to see how to calculate the dominant eigenvalue of a given matrix. Dominant eigenvalue of a given matrix and what is the dominant eigenvector of a given matrix. So, if you want to calculate dominant eigenvalue and dominant eigenvector of a given matrix, then first of all we must know what is the meaning of dominant eigenvalue and dominant eigenvector. So, by the name itself it is clear what is the meaning of dominant eigenvalue. So, it is the largest eigenvalue, but largest means not, suppose 1, 8 and minus 9, 1, 8, minus 9, these are the 3 eigenvalues of the matrix 1, 8 and minus 9. Of course, largest means largest of 1, 8, minus 9 are, suppose I am writing here 1, 8 and minus 9. Suppose these are the 3 eigenvalues 1, 8 and minus 9. These are the 3 eigenvalues. Largest, of course, it is 8 is the largest and minus 9 is the smallest. But no, if we are talking about dominant eigenvalue, we shall talk about the numerically largest or the absolute, take first of all absolute value of the eigenvalues and among those absolute value see which one is the largest. That is the meaning of numerically largest or dominant eigenvalue. So, 1, 8 and minus 9, if you take the absolute value of all these eigenvalues, so modulus of minus 9, that is 9. So, minus 9 here is the dominant eigenvalue. So, it should be clear the meaning of dominant eigenvalue, it is the numerically largest eigenvalue. So, first of all you take the absolute value or modulus of all eigenvalues and see which one is the largest. Which one is largest? After taking the absolute value, then the original one means original lambda I without taking the absolute value, that is dominant eigenvalue. So, I am saying here that 1, 8 and minus 9. So, modulus of minus 9 is 9 and modulus of 1 is 1, modulus of 8 is 8. So, modulus of minus 9 is 9 and therefore, that is 9 is the largest among all these things. So, therefore, 9 is not the dominant eigenvalue, minus 9 is the dominant eigenvalue. So, I believe that idea of dominant eigenvalue should be clear. So, if more generally if you see that A is an n by n matrix and suppose lambda 1, lambda 2, lambda 3, lambda n, these are n eigenvalues of a given matrix A, then lambda 1 is dominant eigenvalue means that modulus of lambda 1 is bigger than modulus of lambda I for all I equal 2, 3, 4, 5 and so on and so forth up to n. That is, if you are taking modulus of lambda 1, modulus of lambda 2, modulus of lambda 3 and so on and so forth, modulus of lambda n, then among all these quantity, modulus of lambda 1 is strictly bigger than all other quantities, all other modulus of lambda I. Then not modulus of lambda 1 is the dominant eigenvalue, lambda 1 is the dominant eigenvalue. So, lambda 1 is called dominant eigenvalue of A if modulus of lambda 1 is larger than, strictly larger than modulus of lambda I for all I is equal to 2, 3, 4 and so on and so forth up to n. Okay. So, if lambda 2 is the dominant eigenvalue means modulus of lambda 2 is bigger than modulus of lambda n, it is also bigger than modulus of lambda 3, it is also bigger than modulus of lambda 4 and so on and so forth, modulus of lambda t is also bigger than modulus of lambda n. And the eigenvector corresponding to the dominant eigenvalue will be called dominant eigenvector. So, what is dominant eigenvector? The eigenvector corresponding to dominant eigenvalue will be called dominant eigenvector. So, I believe that the idea of dominant eigenvalue and dominant eigenvector should be clear to you at this stage, and then we shall see there is a special technique to calculate the dominant eigenvalue of any given matrix. Any given matrix means we are talking about any given square matrix. Before that, this remark is equally important, that suppose the matrix A is given to us, then whether every matrix will have dominant eigenvalue? Answer is no. Every matrix cannot give dominant eigenvalue. So, not every matrix has dominant eigenvalue. So, suppose you take the example that is given here, the matrix is here A 1 0 0 minus 1. Look at here, this is a diagonal matrix. This is a diagonal matrix, and therefore, what are the eigenvalues of any diagonal matrix? Remember here, if any diagonal matrix are given, then eigenvalues are the diagonal elements, number 1. Second is, any lower triangular matrix is given or any upper triangular matrix is given, or that is any triangular matrix is given, then what are the eigenvalues of a triangular matrix? All elements lying on the principal diagonal are the eigenvalues of the triangular matrix. So, diagonal matrix is also a triangular matrix. So, therefore, look at here, eigenvalues of this matrix are 1 and minus 1. 1 and minus 1 are eigenvalues of this matrix A. Which one is the dominant eigenvalues? What is the dominant eigenvalues? Take the absolute value of each eigenvalue. So, modulus of lambda 1 is, that modulus of lambda 1 is 1, modulus of minus 1 is also 1. So, look at here, modulus of lambda 1 is equal to 1, and modulus of lambda 2 is also 1. And what is the meaning of dominant eigenvalue that we have seen? What is the meaning of dominant eigenvalue? See once more. If lambda 1 is a dominant eigenvalue of A, then modulus of lambda 1 has to be strictly bigger than the modulus of all other eigenvalues. Here modulus of lambda 1 is equal to modulus of lambda 2. So, therefore, modulus of lambda 1 is not larger than modulus of lambda 2. There are only 2 eigenvalues here. Therefore, lambda 1 is not an eigenvalue. Again, modulus of lambda 2 is not bigger than the modulus of lambda 1. Therefore, lambda 2 is also not a dominant eigenvalue. Therefore, this matrix A does not have any dominant eigenvalue. So, this shows that every matrix cannot have dominant eigenvalue. Let us see another example. This is again, the matrix A is again a diagonal matrix. Therefore, the diagonal elements will be the eigenvalues of this matrix, and diagonal elements are 2, 2 and 1. Therefore, eigenvalues of this matrix A are lambda 1 equals to, lambda 2 equals to, and lambda 3 is also 1. Therefore, again see that this matrix does not have any eigenvalue, because there are 2 repeated roots. So, modulus of lambda 1 is not bigger than modulus of lambda 2 or modulus of lambda 3, although modulus of lambda 1 is bigger than modulus of lambda 3. But what is the meaning of dominant eigenvalue? If lambda 1 is a dominant eigenvalue, then modulus of lambda 1 should be bigger than modulus of lambda I for all I except from I is equal to 1. So, see that this condition is not satisfied, and therefore, this matrix A does not have any dominant eigenvalue. So, remember now, it should be clear to you that every matrix will not have dominant eigenvalue. Therefore, it will not have dominant eigenvector. Now, we are going to see that suppose there is a matrix A which is having dominant eigenvalue. Okay, this is a very weak condition, I will say, on the matrix A. if we are going to find a dominant eigenvalue of this matrix, first assumption is that A must have a dominant eigenvalue. So, first assumption we are making here, that suppose there is a matrix which is having dominant eigenvalue, and therefore, we are interested to know what is the dominant eigenvalue of this matrix. Okay. And the process, there is a standard process, there is a standard method to calculate the dominant eigenvalue and the dominant eigenvector of a matrix A if the matrix A has a dominant eigenvalue. Therefore, we are making the first assumption of the matrix A is that the given matrix has a dominant eigenvalue, and therefore, it will have dominant eigenvector. So, let us see, if the matrix A has dominant eigenvalue, then how to calculate the dominant eigenvalue and the corresponding eigenvector which will be the dominant eigenvector. So, first step is that choose a column matrix. If A is a n by n matrix, then choose a column vector. Column vector is a column matrix, column matrix. Column matrix means it is a matrix which is having only one column. So, that I am talking about, choose a column vector or column matrix U0, it is always 1, 1, 1, 1, 1 and so on and so forth up to 1. Transpose of this I am writing because it is a column. So, because just to save the time, in fact it is U0 is 1, 1 and so on and so forth up to 1. So, this is our U0. And I am taking here just transpose just to save the space. This is transpose of this row vector. So, this is in fact 1, last one is 1. So, first always you choose the starting vector U0 is 1, 1, 1 and so on and so forth up to 1. Step 1 will be over. Second step is that you compute A into U0. A is the given matrix. So, if A is 3 by 3, then U0 is 1, 1 and 1, that is 3 by 1. So, A into U0 calculate. I believe that you are aware of how to multiply two matrices. So, A is a matrix of order 3 by 3, then U0 will be a matrix of order 3 by 1. So, A into U0 is meaningful. If A is a matrix of order 5 by 5, then U0 will be of a matrix of order 5 by 1, that is U0 will be 1, 1, 1, 1, 1, 5 times 1 will be there. Okay. So, first step choose U0, second step is that you calculate or compute the product of the two matrices A into U0. So, look at here, if A is 3 by 3, U0 is 3 by 1, so A into U0 will be 3 by 1, again will be a column vector. So, A into U0 will be calculated. Okay. Third step is equally important, and perhaps I have explained that if A into U0 you are going to calculate, you will get a column vector, and this column vector or this column matrix must be normalized. I am saying must be normalized. What is the meaning of this one? Third step is normalize the matrix A into U0, and A into U0 is now a column matrix. So, if A is n by n matrix, then U0 is a matrix of order n by 1. Therefore, A n by n into n by 1, so it will be n by 1. So, A into U0 again will be a matrix of order n by 1. So, therefore, normalize the column vector or the column matrix A into U0. How to normalize, and what is the meaning that this column vector is in the normalized form. Okay. So, suppose that you are having a vector 1, 2, 3 coming from R3, 1, 2, 3 simply, triplet 1, 2, 3 coming from R3, R cross R cross R, whether it is in the normalized form or it is not in the normalized form. So, the largest element or the largest entry in this vector 1, 2, 3 must be 1, largest. Here 1, 2, 3, largest is 3. So, it is not in normalized form. So, therefore, divide this vector by the largest quantity, largest entries from here. So, 1, 2, 3, 3 is the largest. So, divide this vector by 3. So, what we will get? First one which was 1, 2, 3, now we will get 1 by 3, 2 by 3 and 3 by 3. So, 1 by 2, 1 by 3 and 2 by 3 and 3 by 3, 3 by 3 is 1. So, look at here, the largest is 1. So, now this one is in the normalized form. So, if x1, x2, x3, xn, this is n tuples. If it is not clear, let me explain first of all on blackboard, so that it will be idea will be clear what is the meaning of normalized form. Okay. I am saying that suppose I am taking this vector 0, 2 and 4. This belongs to R3. Okay. Suppose U is it in normalized form or it is not normalized form. See the entry 0, 2 and 4. The largest entry should be 1. So, largest entry is here 4, therefore, it is not in the normalized form. So, how to make this one normalized? So, highest is 4, so divide this u by 4. So, in another quantity you will get v is your u by 4 means 0 by 4, that is 0. 2 by 4 means this is your 2 by 4 and then 4 by 4, that is 1. And look at here, this again belongs to R3, this is an element of R3, largest is 1. Therefore, this vector v is in normalized form. So, if the vector is in normalized form, it is well and good. If it is not in normalized form, we will have to transform this one into normalized form. So, suppose I am taking here another vector u again, so some other u1 is -8, -7 and then 15, or let me say here 2. Look at here, again the largest quantity is 2, it is not in the normalized form. So, what we will do here? If you take the absolute value, largest has to be 1. So, what I will do here? We will get another element v1 and v1 is u1 over minus of 8. So, I shall divide everything by -8. So, -8 over -8. So, -8 over -8, again -7 over -8, then again 2 over -8. So, see what we are going to get here, 1 -8 over 1 minus plus 7 by 8 and then minus 2 by 8, so -1 by 4. So, look at here, the largest is 1, largest quantity, largest entry is here 1. Therefore, this vector v1 is in the normalized form. Okay, so I believe that the idea of a vector which is in normal form or normalized form, it should be clear. So, in the power method we shall see that a into u0, if you are going to calculate whether it is in the normalized form or it is not in the normalized form. If it is in the normalized form, it is well and good. If it is not in the normalized form, normalize it. And this vector, this look at here, here I have divided by 4 and this 4 is called normalizing factor. Okay, this 4 is called normalizing factor. Here -8 is the normalizing factor. So, this with the help of this -8, this u1 has been normalized. Here with the help of this 4, this u has been normalized. So, this here in this case 4 is the normalized factor, here -8 is the normalizing factor, and therefore, this normalizing factor is going to play an important role in power method for calculating dominant eigenvalue and dominant eigenvector. So, at this stage we are aware that if the given vector is in normalized form or it is not in the normalized form, if it is not in the normalized form, how to normalize it. So, step 3 is that after computing a into u0, see a into u0 it is in the normalized form or it is not in the normalized form. If it is not, then normalize it by dividing each component by the largest in magnitude. This is very important, largest in magnitude. So, in the second example we had seen that -8 was the largest in magnitude after taking the absolute value. So, divide that vector throughout by the largest quantity which is in largest in magnitude. The resulting vector will be automatically in normalized form. Then you repeat the first two steps. What are the first two steps? Is calculate A into U0 and then you normalize it with the help of normalizing factor. Okay. And continue, repeat this step. Fine. Step 2 and 3, then the normalizing factor. What is the meaning of normalizing factor? By which we are making the column factor in the normalized form. That is your normalizing factor. That normalizing factor is the dominant eigenvalue, and the final vector is the corresponding item. The final vector will be the dominant eigenvector. Perhaps if it is not clear, look at here. In one of the example, what we are making the given vector A into U0 into normalizing form. With the help of that, you divide that factor by the quantity, by the entry which is largest in magnitude. So, see that is there any change in the normalizing factor after some step, after 3 steps or after 8 steps or after 10 steps or so. When the change in the normalizing factor is negligible, when change in the normalizing factor is negligible, see that normalizing factor is coming in 2, 3, 4 steps after same. The change in the normalizing factor is coming to be very, very negligible, almost it is coming to be same. Then stop the process and see that normalizing factor will be eigenvalue, dominant eigenvalue, and the corresponding final vector A into Ui will be the dominant eigenvector. Let me give one example, then this idea will be clear. Okay. Suppose this example, the matrix A is given to us. Okay. Matrix A is given to us. Then we are interested to know what is the dominant eigenvalue of this matrix and that what is the dominant eigenvectors of this matrix. So, step 1 is that choose the vector U0 as 1, 1, 1. Okay. See slowly and slowly. The matrix A is given. Step 1 is that choose U0 as 1, 1, 1. I am writing transpose just to show that in fact it is a column matrix or column vector. Second step is that compute A into U0. A into U0, Y1 I am calling here, Y1 is equal to A into U0. So, Y1 A into U0, this matrix is A and this U0 is 1, 1, 1. Now, this is a column matrix. Okay. So, multiply these two matrices. See that, I believe that you are aware of how to multiply two matrices. See that output is 5, 22 and 5. This is your A into U0. So, this the final matrix 5, 22 and 5, check whether it is in normalized form or no. See that largest quantity out of this 5, 22, 5 is 22. Therefore, it is not in the normalized form. We will have to make this one normalized form. How to make? Largest is 22. So, therefore, divide every quantity by 22. So, 5 by 22, 22 by 22 and 5 by 22. So, this 22 will be called normalizing factor. Okay. So, look at here, we are going to, and this Y1 I am going to Y1 by 22, divide this factor, this vector Y1 by 22, see what you are going to get. Look at here, this M1 is equal to 22, this is normalizing factor, and therefore, divide Y1 by 22. So, that I am calling here U1, U1 is your Y1 by 22, this is your 5 by 22, 1, 5 by 22. See that it is 0.22727, 1 and this. See that, of course, transpose I am writing just to save my space, this is the column matrix. So, largest is here, look at it, largest is 1, largest is 1. Therefore, U1, this vector U1 is in the normalized form. Okay. Then, what is the next step? Repeat these two steps. Then calculate what is the next step? Calculate A into U1. A into U1. A is the same matrix for which we are interested to know the dominant eigenvalue. So, next step is again repeat steps 2 and 3, we are going to repeat. So, compute y2 is equal to a into e1, e1 is should be always in the normalized form. So, again a into e1, look at here, e1 is 5 by 22, 1 and 5 by 22. Multiply, we are going to get this one, 21 by 11, 225 by 11, 22 by 11. If you see this one, it is in fact 1.90901, 20.45456, 1.90901 transpose of this. Again look at here, again this vector y2, that is a into e1, it is not in the normalized form. Means because the largest quantity is 20.45456. Therefore, we will have to make again this vector y2 in the normal form. And how to make in the normal form? Divide this y2 by the largest quantity 20.45456, and this is again a normalizing factor. Okay, we will have to see that what is the meaning of dominant eigenvalue. We will have to keep a watch on this normalizing factor. If there is no change in the normalizing factor, no change means the change is negligible in the normalizing factor, we shall stop the process. If the change is large, we shall continue these 2 steps. So, earlier remember in the first step normalizing factor m1 was 22, at this stage 20.45456. So, therefore, divide this y2 by 20.45456, see that again you will get another vector of u2 which will be in the normal form. So, let us normalize y2. Look at here, m2 is this 225 element, that is 20.45456. This is our normalizing factor. Normalize y2. So, u2 will be y2 by m2. See that you are going to get here 0.0933331 and this quantity. See that again here the largest quantity is 1. Therefore, again it is in normal form. Very simple process. What is the next step? Compute a into u2. Compute u2 is calculated, therefore, again calculate a into u2. So, let us see what is a into u2. So, a into u2 calling here y3, calculate. See that again y3 is in normal form or no. If it is not, divide by its the highest quantity which is coming in a into u2 and continue this process. I have not calculated all steps. See that y7 is a into u6, a into u6 is coming to be this. Again y7 is not in the normalized form because highest is 20.12412. Therefore, normalize y7. Therefore, m7, what is the normalizing factor? m7 is this one, 20.12412. This is your normalizing factor. This is your normalizing factor. Therefore, u7 is, divide this y7 by m7, you are going to get this. Again look at here, 0.06202, 1, 0.06202. So, again highest quantity is here 1. Now, it is in normalized form. The moment is in normalized form, calculate again a into u7. A into u7, see what happens. Remember here m7 we had started m1 by 22, then m2 was 20 point something. Again see that what is m3, m4, m5, m6 and so on and so forth, that is the normalizing factors. m7 we are getting here 20.12412. Okay, m7. Now, after that we shall calculate a into u7 and see what happens. Now, calculate y8 is a into u7, it is again 20.12404. Look at here, this is the highest. So, again m8 is 20.12404. Highest, the m8 is this, the highest quantity, largest quantity. So, m8 is this, calculate again u8, u8 is y8 by m8 and see that again it is coming to be this. So, m8 is 20.12404. And what was m7? m7 was also little similar. m7 was 20.12412, 20.12412 and m8 is 20.12404. So, 124 up to it is similar. So, look at here, in m7 and m8 both are almost same. These normalizing factors, the difference in the normalizing factor becomes negligible. So, therefore, we shall stop the process, we shall call here that m8 is the dominant eigenvalue, m8 the dominant eigenvalue and the corresponding final eigenvector u8. This u8 is the dominant eigenvector. Remember, calculate M1, M2, M3, M4, M5 and so on and so forth. See that difference between these Mi when it becomes negligible. You stop the process, that final Mi will be called the dominant eigenvalue, and the final vector u will be called the dominant eigenvector. So, look at here, M at 20.12404, it is the dominant eigenvalue, and this u at, that is 0.062021 and 0.06202 transpose of this is your dominant eigenvector. In this fashion, we can calculate dominant eigenvalues and dominant eigenvector of any given matrix. I shall give one more example, so that idea of calculating dominant eigenvalue and dominant eigenvector must be clear. It must be crystal clear, in fact. So, again look at here, this matrix A is given to us. We are interested to know what are the dominant, or what is the dominant eigenvalue of this matrix and the corresponding dominant eigenvector. Second, age step 1, as usual, choose u0 as 1 1 1. So, u0 we have chosen 1 1 1, transpose of this row vector. Transpose of this row vector is a column vector. Second step is compute y1 is equal to a into u0, a into u0. Okay, a into u0, that is y1, a into u0. Look at here, we are getting here 315, 315. 315, it is not in the normalized form. Therefore, here 5 is the, out of 315, 5 is the largest. Therefore, make y1 to be in the normal form. So, divide this y1, y1 by 5. So, you will get u1, you will get u1 to be in normal form. So, u1 will be equal to y1 by 5, and this 5 is the normalizing factor. So, let us see the next step. M1 is 5. I have explained what is the meaning of this M1 normalizing factor. See that u1 is y1 by 5, that is 3 by 5, 1 by 5, 5 by 5, that is 0.6, 0.2 and 1, transpose of this. So, u1 is in the normalized form. Okay, because highest is 1 here, highest quantity, and therefore, second step is calculate a into u1. Calculate a into u1. See what happens. A into u1, y2 is a into u1, again a is the given matrix, u1 is this. See that a into u1, that is y2, we are going to get 1 1 2.20. So, again y2 is not in the normalized form, because highest is 2.20. Therefore, make y2 in the normalized form. So, divide this y2 by 2.20, you will get u2, that will be in the normalized form. So, let us see the next step. M2 is now 2.20. First of all, M1 was 5. Look at here. M1 is 5. First, M1 is 5. At the second stage, M2 is 2.20. Look at here. These MIs are going to be finally converted into dominant eigenvalue. So, it was 5. Now, it is coming to be 2.20. So, U2 is y2 by M2. Look at here. 0.45, 0.45 and 1, transpose of this. So, now this vector is in the normalized form. Okay. Then continue this process, means now calculate a into u2. See what happens. If it is normalized form, it is well and good. Otherwise, you convert this vector again into normalized form. This vector means is a column vector or column matrix into normalized form, and continue this process till that the changes in MIs becomes negligible. Let us see how. If you are calculating M1, M2, M3, M4, E1, U2, U3, U4, and then see that this chart, this table you will see. U0 we have taken 1 1 1, that was the first step. U0 is 1 1 1. Second step is U1. U1 is with the help of M1. M1 it was in first step, if you remember 5, U1 is 0.6, 0.2 and 1. All these UIs must be in the normalized form. See, when M2 is 2.20, then we have seen that U3 is 0.45, 0.45 and 1. Third step, if you go through, M2 will be 2.82 and U3 will be 0.48, 0.55 and 1.0. We shall stop the process when the change in MIs will be negligible. Here it is, M1 is 5.0, M2 is 2.20, 2.82. Look at here, there is a big change. Therefore, we cannot stop the process. See, then calculate. See that in the next step, M4 is 3.13. M3, not M1, M2, M3, M4 is 3.13 and U4 is 0.51, 0.51 and 1.0. So, again from 2.82 M has changed to 3.13. So, again we cannot stop the process. Go next step, see that M5 is 3.02 and then U5, corresponding U5 is 0.50, 0.49 and 1.0. See the next step, now 3.02, next step is M6 is 2.99. Okay, and then U6, corresponding U6 is 0.5, 1.0. Take one more step, see that M7 is 3.00 and U7 is 0.50, 1.0. See the very interesting result. M1 starting from 5, it is coming 2.20, 2.82, 3.13, 3.02. Look at here, 3.02, 2.99, 3.00. It becomes almost negligible, 2.99 and 3.00. So, you shall stop the process. So, see that this M7 that is equal to 3, it is dominant eigenvalue of the given matrix A, and this U7 that is 0.5, 0.5 and 1.00, this is called the corresponding eigenvector, that is dominant eigenvector corresponding to M7 is equal to 3.00. So, therefore, final conclusion is that this M7 is equal to 3 is the dominant eigenvalue and U7 is the dominant eigenvector. So, final conclusion is recorded in this slide. Dominant eigenvalue is M7 is equal to 3.0 and dominant eigenvector is U7. So, I believe that if any matrix is given and if this matrix has a dominant eigenvalue, then with the help of this power method, we should be able to calculate the dominant eigenvalue and the dominant eigenvector. So, that was the basic purpose of this lecture, how to calculate dominant eigenvalue and dominant eigenvector of a matrix if it has a dominant eigenvalue and dominant eigenvector. Thank you. I will stop this class here.